Look at the planet spinning on its side, its rings standing vertically like a hoop you'd roll along a sidewalk. No other world in the solar system does this, and every physical law you'd reach for to explain it seems to fail here. Uranus is the great exception in our cosmic neighborhood, and it's been hiding that secret for 4.5 billion years. Its magnetic field, too, is broken in ways we've never seen anywhere else, lopsided and tilted so far off-center that it switches on and off as the planet rotates, and the single spacecraft that ever flew past it, in 1986, answered almost nothing. Voyager 2's brief visit left us with a pile of contradictions so deep that a scientific generation has been arguing about them ever since. We thought we understood ice giants. We thought the architecture of our solar system had a tidy logic we could map out like a blueprint. Uranus refuses every one of those rules, and in doing so, it's quietly rewriting what we think we know about how worlds are made. But to understand why Uranus broke every rule, we first have to see what those rules were. The blueprint. Our solar system has a story that feels almost designed, an orderly procession moving outward from the sun. Closest in sit the rocky worlds, small, dense, scarred by craters, forged from metal and stone in the furnace of the young star. Beyond them stretch the gas giants, Jupiter and Saturn, vast ballooning masses of hydrogen and helium, seizing the leftover gas before the sun could blow it away. Further still, in the deep cold where the sun's light barely reaches, the material changes character. Out here, the building blocks weren't rock, so much as ice, water ice, methane ice, ammonia ice, and the worlds that formed here grew huge by gathering it up like slow-moving collectors. That's the class Uranus was born into, what we now call the ice giants. By all accounts, Uranus should fit this pattern cleanly. A calm, orderly giant spinning upright on its axis, like every well-behaved planet around it. The rules of formation, the flow of the early solar system, the physics of a spinning cloud collapsing into a world, they all point the same direction. What nobody knew at the time was that Uranus had already been shattered. The discovery. On the night of March 13, 1781, a German-born astronomer named William Herschel was sweeping the sky with a homemade telescope from his garden in Bath, England. He found a faint greenish dot that moved against the fixed stars, and at first he assumed it was a comet. Over the following months, astronomers watched it track a nearly circular path, and the truth slowly settled in. Herschel had discovered a planet. It was a revelation without precedent. The known solar system doubled in a single stroke, and the young United States of America was barely 5 years old when humanity first realized this world existed at all. But almost immediately, something troubled the observers. Uranus refused to follow the path the mathematicians predicted, shifting ahead of schedule, then lagging behind, as if some invisible hand were tugging at it. Those orbital wobbles would eventually point the way to Neptune, a planet found with math before it was found with a telescope. But the mystery of Uranus went far deeper than a few irregularities in its path. For 200 years, every telescope that turned toward it saw only a smooth, unmarked, pale blue disk, revealing nothing at all about what might be happening beneath. But the real strangeness wasn't its orbit, it was what lay beneath that pale disk. The sideways world. Because measure the tilt of Uranus, and something is terribly wrong. Its axis leans 98 degrees, rolled almost flat against the plane of its orbit. Every other planet spins nearly upright, tops on a table, and Earth tips a modest 23.5 degrees. Uranus doesn't spin like a top at all. It wheels around the sun like a marble caught in a groove, its north pole pointing off sideways into empty space. The consequences take generations to unfold. One Uranian year lasts 84 Earth years, which means each season stretches on for 21 years. For 42 straight years, one pole stares into the sun, bathed in a light that never fades, while the opposite pole sits in a darkness just as long, a single night that outlasts entire human lives. No weather on any other world has ever had to answer to that. Astronomers looked at this sideways world, and the only question worth asking was how it ever happened. And this is the part where things stopped being simple. The collision hypothesis. The leading theory is simple to say and almost impossible to imagine. Somewhere in the solar system's violent infancy, roughly 4 billion years ago, a body the size of Mars or Earth slammed into the young Uranus and knocked it over. Not a glancing scrape. A collision carrying so much angular momentum that a world's entire axis of rotation was wrenched sideways and never straightened. Computer simulations have rebuilt the moment thousands of times. Over 50 impact scenarios run on supercomputers, each one smashing 2 planets together to find the blow that leaves behind a rolling ice giant. The impactor was probably icy itself, 1 to 3 times the mass of Earth, meeting Uranus at just the right angle to tip it rather than tear it apart. When the dust settled, most of that mass had merged with the planet it struck. Most of it, but not all of it. A collision that violent has consequences that do not quietly disappear. It scatters debris into orbit. It melts and reshuffles a planet's interior. It leaves heat behind in places heat has no right to be. Witnesses, in other words. But if that impact happened, it should have left a trail, and for decades, we couldn't find one. The missing evidence. An event on that scale should have left the system scarred and disordered. A debris disk far heavier than anything we see today. Moons jumbled into eccentric, backward paths. A planet still glowing with the heat of its own destruction. What astronomers actually found in 1986, when Voyager 2 swept past, was the opposite of all of it. Uranus's moons orbit in neat, nearly circular paths, all tipped to match the planet's own strange tilt, as if the great catastrophe had somehow produced perfect order. The debris disk, that should have weighed 100 times more than the moon system we see, was simply not there. And the planet itself runs cold, radiating barely more heat than it receives from a distant sun, as though nothing violent had ever touched its interior. The evidence had the shape of an impact without the fingerprints of one, and for years the hypothesis hung by a thread. If the solar system's least cooperative world refused to confess, then the story would have to find a different ending entirely. This is where the story takes a turn nobody expected. The moons remember. Planets forget. They get worn smooth by 1 billion years of impacts and weather, their surfaces rewriting themselves until the record of their birth is gone. But moons are more stubborn. Uranus holds 5 major moons, and when astronomers examined their orbits, every single one told the same story. They circle the planet directly above its equator, moving in near-perfect circles that lie exactly in line with the planet's own spin. That narrow, orderly band is not something you stumble into by chance. It is the signature of formation inside a flat disk of debris, the kind of disk left behind when a collision melts a world and spits the wreckage out into orbit. Lay that pattern against the timing of the Great Tilt, and the sequence falls into place. The moons condensed from the cloud of shattered rock and ice that the impact threw into space, settling into a stable ring around the ruined planet. What Uranus's surface could not confess, its children remembered and wrote down in their orbits. But the moons only told half the story. The magnetosphere told the rest. The broken field. When Voyager 2 swept past Uranus in January 1986, its instruments did not find what they expected. On Earth, Jupiter, Saturn, every magnetized world we knew, the field rises from deep inside the planet, a tidy dipole aligned with its spin axis. Uranus's field refused the pattern. It was tilted, not a little, a full 59 degrees off the pole, so far that it swept sideways into the planet's rotation instead of around it, and it was not centered on the planet's heart. The field's actual source sat a third of the way out toward the surface, as if the planet's magnetic engine had been pulled loose and shoved into exile. That tells you something startling about the interior. The field cannot come from a solid iron core, because a core that small and that deep could not produce a field this restless. Instead, it must be generated in a shell of compressed material far out from the center, under forces that have no counterpart anywhere else in the solar system. And what that field revealed is something we're still trying to fully grasp. The ice mantle. Peel Uranus open and you find nothing like the worlds we've mapped before. At the very heart sits a small rocky core, maybe a fifth of the planet's mass. Above it stretches the real bulk of the world, a vast mantle of ice. But not the ice in your freezer. Down there, pressures reach millions of times Earth's atmosphere. Water, methane, and ammonia get crushed so hard they stop being separate molecules and turn into something we call hot ice, a super-dense fluid with the electrical conductivity of a metal. It does not melt like ordinary ice. It simply churns, charged and mobile, billions of tons slipping against itself under a roof of crushing weight. That circulating, electrically alive mantle is what breaks the planet's magnetic order. Any churning, conductive fluid can generate a field, and when its motion is as chaotic as this, the field it makes is deformed and eccentric, tilting wildly off-axis. The strange magnetosphere is not a glitch. It is the direct readout of a vast, exotic ocean under pressure. But Uranus wasn't done defying expectations, not even close. The temperature paradox. Uranus is the coldest planet in the solar system, colder even than Neptune, which sits 1 billion kilometers farther out. That alone breaks every rule of thumb. But the deeper strangeness is invisible to a thermometer. Voyager 2's infrared eyes found that Uranus radiates back almost exactly as much energy as it receives from the Sun, a ratio of roughly 1.06 to 1. Neptune, its near twin, pumps out more than 2.5 times the sunlight it takes in. Jupiter and Saturn do the same. Every other giant planet is still slowly bleeding the heat left over from its birth, glowing faintly in the dark like a dying ember. Uranus barely gives anything off at all. In astronomical terms, it's thermally dead, sitting in near-perfect equilibrium with the sunlight that only grazes it. What nobody knew at the time was that the collision had stolen something we thought every planet kept: the lost heat. How do you lose a planet's internal heat? Two ideas circle the scene of that ancient accident. The impact that knocked Uranus onto its side may have literally ruptured its shell, venting the primordial warmth like steam escaping a tear. Or the blow scrambled its layering, turning the mantle into a sluggish, stratified sea where hot material no longer rises and cold no longer sinks. Convection, the slow churn that carries heat outward in every other giant, simply stopped. What's left is a planet in hibernation, a core that's still warm but sealed off, its surface growing colder for billions of years. Even today, Uranus leaks only 1/5 as much heat per square meter as Neptune does. The engine that should drive weather, storms, motion is quiet. A planet should not be this still. But the cold wasn't the strangest inheritance from that ancient collision. The atmosphere. And so the pictures came back pale, almost empty. Against a backdrop of banded giants, Uranus hangs as a smooth, featureless disk of cyan, the color of a cloudless sky at high altitude. Methane at the top absorbs red light and scatters blue, painting the whole world in one muted shade. Beneath it, a hydrogen and helium envelope, roughly 83% hydrogen, 15% helium, and about 2% methane, quietly stores the sunlight it does receive. There are no belts, no zones, no great spot, no storms. Voyager 2 counted 10 cloud features across the entire planet, a wisp or two where the other giants show an endless collision of currents. The atmosphere is stable to the point of stillness. With no internal heat to stir it, even that faint circulation runs almost entirely on sunlight. For one brief flyby, Uranus looked like a painted ball, serene, silent, finished. And this is the part where timing became everything. The flyby window. Voyager 2 didn't arrive at Uranus by accident of generosity. It flew past in 1986, and 1986 happened to be solstice, the single most extreme moment in an 84-year cycle. One pole faced the sun dead on, and the other was plunged into decades of night. On a planet tilted 98 degrees, that's not a season. That's a world holding its breath. A solstice atmosphere is the most quiescent state a tilted world can reach. The sunlight barely grazes, the circulation stalls, and every feature smooths into stillness. We photographed a planet in its deepest trance. For 84 years, the light at the poles never changed, and neither did the weather book we wrote from it. But decades later, when the seasons finally changed, so did the planet. The awakening. Turn the calendar forward to the 2000s. Hubble starts watching Uranus as it crawls toward equinox, and the serene painted ball isn't serene anymore. Massive storms flare across both hemispheres. Bright cloud bands wrap the globe where 1986 showed nothing but blank blue. Keck resolves structures that Voyager could never have imagined. What looked like a finished, quiet planet turned out to be a planet at its most dormant. Given fresh illumination at new angles, the atmosphere began to churn, billow, and reorganize itself. The featureless world of the flyby became a weather machine, throwing fresh storms every few years. This is where the story takes a turn nobody expected. The storm systems, and these aren't gentle squalls. Some of Uranus's storms stretch across whole continents, vast bright caps that erupt, wander, and vanish within weeks. Their power traces straight back to that 98-degree tilt. As the axis swings, one hemisphere bakes in continuous daylight while the other freezes in darkness, and the atmosphere has to shunt enormous energy between them. That transfer is chaotic and uneven, unloading in sudden surges that can roughly double the brightness of a cloud feature in a matter of days. The planet doesn't calm down so much as retune itself. But the atmosphere was only the surface. The real mystery lay thousands of miles below. The diamond rain. Down where the pressure reaches millions of atmospheres, methane begins to break apart. Its carbon atoms separate from the hydrogen holding them, then pile onto one another in layer after layer of graphite and crystal. The result is a slow, silent hail of diamonds falling through the liquid interior, each one no larger than a grain of sand, but some maybe a millimeter across. Lifted and chilled and sunk again by the churning of the mantle, they tumble for thousands of miles before anything stops them. We know this isn't idle speculation because we've done it in the lab. Firing lasers into plastics seeded with methane, researchers have watched carbon forge itself into miniature gems at a fraction of the pressure Uranus exerts on its own depths. Somewhere far below the clouds, the whole planet may be dressing itself in falling treasure. And if that sounds extreme, the conditions deeper still are beyond anything we've recreated on Earth. Supersonic ice keep descending, and the liquid itself changes character entirely. Water stops behaving like a fluid and settles into a solid where oxygen atoms lock into a rigid lattice, a lattice that stays put while hydrogen ions slip freely between the gaps. That is supersonic ice, a substance that conducts electricity like a metal while holding its shape like a crystal. It is not something we've found in any quantity on Earth. Its closest natural habitat is the inner workings of ice giants. And here is the strange part. That freely flowing hydrogen is exactly the kind of charged fluid that generates enormous magnetic fields. It is not uranium's core that whips its magnetic cocoon into such wild contortions, but this exotic, electrified water swirling far above it. One more layer of the planet explained. But Uranus wasn't done yet, not even close. The ring system. Beyond the atmosphere, a thin family of rings waits, 13 faint bands circling the planet almost invisibly. They are narrow, dark, and so unreflective they seem to swallow light rather than return it. And for most of human history, we had no idea they existed. They were only discovered in 1977, by accident, when astronomers watching a distant star pass behind Uranus noticed it flicker again and again before the planet even reached it. Each blink was a ring crossing in front of the star. The rings themselves reflect barely a few % of the sunlight that touches them, which is why they stayed hidden so long. And a ring that reflects almost nothing is a ring made of something dark, dusty, and far from fresh. It is a fragile arrangement, a balance between the pull of moons and the pull of the planet itself, and it cannot last forever. What nobody knew at the time was that the rings were dying. The shepherd moons. The rings do not hold their shape on their own. They are steered, pinched, and kept in place by a pair of small moons named Cordelia and Ophelia, one tucked inside the epsilon ring and one just beyond it. Their gravity does what a planet's gravity alone cannot. By tugging at the ring's edges, they sweep up stray particles and confine the material into a band no wider than a dozen kilometers. Without them, the ring would spread, thin out, and vanish into the darkness around it. That arrangement is a balance beam set on a pin. A moon pushing too hard scatters the ring. A moon drifting a few kilometers changes the shape of the whole system. Every pass of every orbit has to stay within a razor-thin margin of exactly the right pace. But the rings themselves were only part of a much larger debris field. The moon families. Uranus carries 27 known moons, and they fall into 3 families that could not be more different in their origins. The 5 classical moons, Titania, Oberon, Umbriel, Ariel, and Miranda, are large enough to be round worlds in their own right. Closer in sit the small shepherds that hold the rings, and far out drift a scattering of captured objects, irregular moons that orbit on tilted, stretched paths. Each family tells a separate history. The captured moons were taken from somewhere else, snared by Uranus's gravity, and never let go. The inner shepherds are crumbs from the same cloud of debris that made the rings, and the 5 classical moons should be clean, settled bodies, formed in place and left in peace. That is what the models predicted anyway. When Voyager 2 finally got close enough to see the classical moons in detail, the surfaces broke every expectation. These were not the smooth, cratered worlds the textbooks described. And this is the part where things stopped making sense. Miranda's scars. Start with Miranda, the smallest of the 5 classical moons, barely 470 kilometers across. Its surface is a patchwork of steep cliffs and terraced sunken plains called coronae, a jigsaw assembled from pieces that do not fit. One cliff face, Verona Rupes, drops more than 20 kilometers straight down, some of the tallest topography found anywhere in the solar system, pressed into a moon you could drive across in a day. The canyons cut across older crater fields, and the coronae look stamped into the crust as if something pushed up from beneath. The surface reads like a world that was shattered, its fragments collected and fitted back together by a hand with no patience for neatness. Geologists have argued for decades over what did the breaking and the rebuilding, and no single answer has ever satisfied everyone. But Miranda wasn't the only moon carrying scars from the deep past. Ariel's canyons. Ariel is a different kind of memento. Its surface is young, far younger than a moon its size should be, crisscrossed by rift valleys so vast they'd swallow whole mountain ranges. Bright deposits lace those canyon floors, material that looks poured rather than carved, and the best explanation is cryovolcanism, water and ammonia erupting as slush and freezing where it lands. That takes heat. Ariel had no business staying warm long after the deep freeze should have claimed it, and yet the evidence is plain. Something held Ariel's interior open, kept it kneading and stirring when the rest of the system lay dormant. This is where the story takes a turn nobody expected. Tidal heating. The word for that hidden furnace is tidal heating, and it works, of all things, through timing. When one moon completes its orbit in a neat fraction of another's, gravity pulls on both in a steady rhythm, stretching each orbit into an ellipse and flexing the rock and ice beneath. All that flexing turns into friction, and friction turns into heat, enough to keep an interior molten for billions of years. Jupiter's Io is the textbook case, a world so tormented it erupts more lava than all of Earth's volcanoes combined. Saturn's Enceladus does the same trick under its frozen crust, venting geysers through cracks in the ice. The cruel joke is that the moons of Uranus should have been the perfect candidates. The geometry was there, the pull was there, everything that makes the trick work was lined up. But Uranus's moons weren't locked in resonance anymore, they'd escaped. The lost resonances. Escaped, yes, but not always. Somewhere in the deep past, Miranda and Ariel did hold each other in resonance. And while they did, tidal forces ran wild, heating them, reshaping them, writing scars across their surfaces. It's a far quieter system now. Over billions of years, the arrangement drifted, a slow gravitational settling that pulled the moons out of lockstep and let the kneading stop. The ice froze, the eruptions wound down, and the worlds went still. But the record of that wild era stayed etched in stone, preserved like rings in a cross-section of a tree. Every canyon and ridge we study is a fossil of a time when these moons were alive with motion, a chapter closed so long ago that even the heat remembers it only faintly. And what that era left behind is something we're only beginning to map. Umbriel's darkness. Somewhere out in that dark arena sat Umbriel, and it was the moon the artist forgot to paint. Walk a whole world, and every horizon reads the same. One crater after another, so tightly packed, the surface looks raw and unfinished. Geologists call it crater saturation, and it means Umbriel stopped evolving early. No resurfacing, no volcanic repaint, just an ancient face worn into a static pattern of impact scars. It is the darkest major moon orbiting Uranus, reflecting barely a fifth of the sunlight that reaches it. The one feature that breaks the monotony is a single bright ring inside a crater named Wonder. Nothing else lights the dark. The rest is a landscape that decided long ago to stop changing, and it has kept that promise for billions of years. But the strangest moon wasn't Umbriel, it was the one farthest out. Oberon's age, past Umbriel, almost twice as far out. Oberon rolls through the quiet. It carries more craters than any companion in the system, and many of those floors are coated in a mysterious dark material no one expected. The signature looks like organic compounds, perhaps carbon-rich dust left behind by ancient impacts. Whatever it is, it drapes over the lowest ground, collecting in the shadows like sediment in a dry sea. Set the clock back 4 billion years, and this surface looks mostly as it does tonight. Oberon is the oldest landscape in the Uranian system, a time capsule from the solar system's youth when collisions were relentless and every world wore a fresh, battered face. Nothing has wiped it clean since. But Uranus wasn't done yet, not even close. Titania's faults. Titania is the largest of the moons, and she bears the marks of a different kind of violence. Great fault scarps, some stretching for more than 1,500 kilometers, slice across her crust like cracks in old porcelain. The story reads backward. As an ocean within her interior froze and expanded, the surface had nowhere to go. It buckled, it split, and it threw up mile-high cliffs where the crust tore itself apart from the inside. Those scarps are why Titania feels less like a barren rock and more like a world with a damaged past she is still carrying. The frozen interior that did this is still there, deep beneath us, holding the fractures open at a scale we can barely picture from orbit. And this is the part where we realized Uranus's entire system was a laboratory. The irregular moons. Past the 5 great moons, a scatter of small bodies circles Uranus at distances of millions of kilometers out. 10 irregular satellites have been found so far, and one detail stands out immediately. 9 of the 10 orbit backward, in retrograde, along paths so steeply tilted they cut almost vertically across the whole system. The reason is not hard to guess. These are not moons in the way the others are. They are captured asteroids and Kuiper belt drifters, wanderers that drifted too close in the early solar system's chaos and were seized by gravity. The first 2 found, in 1997, are Caliban and Sycorax, barely 60 and 30 kilometers across, each a faint reddish smudge of rock. That redness is the clue. It ties them to the icy bodies scattered beyond Neptune, so each one is a preserved record of the old solar system, its migrations and collisions, frozen into a rock no bigger than a city. They are not Uranus's family at all, only interlopers with a stolen history, but the moons only mattered because of what we found between them. The magnetosphere. Now come back to the space between those moons, because what Voyager 2 measured there rewired how we think about planetary magnetism. Every planet with a magnetic field lines that field up with its spin axis within roughly 11 degrees. Uranus breaks that rule completely. Its field tilts 59 degrees away from the rotation axis, and it is not born where a proper field should be born. Rather than centered at the core, its source sits offset by nearly a third of the planet's radius, displaced toward the southern hemisphere. Nothing else in the solar system even approaches this. Nothing. The dipole itself runs 50 times stronger than Earth's, yet none of it behaves the way the models demanded, and every plot of the data came back lopsided, skewed, stubbornly asymmetric, no matter how it was arranged. What nobody knew at the time was that the field wasn't stable. The plasma environment, the charged particle environment that field builds, is stranger still. Voyager 2 found a magnetosphere nearly empty of plasma, densities below 3 particles per cubic centimeter, a fraction of what fills Earth's own. They called it a vacuum magnetosphere, and for decades nobody could explain how so much nothing stayed so hostile. The solar wind slams head-on into that hollow shield, and because the field is tilted and off-center, the point of collision shifts with every rotation. As the planet turns through its 17-hour day, the whole magnetosphere swings, and the long magnetotail trailing behind it coils into a corkscrew. Riding that twisted structure are radiation belts of trapped electrons and protons, intense for reasons no one could reconcile with a system this drained. It was as if the emptiness itself had a hidden engine keeping everything on edge. Every answer the flyby handed us raised a fresh contradiction, and the closer we looked, the less any of it held together. And this is the part where things stopped being predictable. The auroras. When Hubble turned its eye on Uranus, it found lights where no lights should be. Auroras, ghostly glows of ultraviolet energy, flickering high above the cloud tops. On Earth, auroras ring the poles, tied to our magnetic poles like a crown. Uranus breaks that pattern completely. Its magnetic field is so wildly offset, tilted more than 59 degrees from the axis of rotation, that the auroras don't anchor to the poles at all. Instead, they wander. They drift across the planet's surface, lighting up regions that have no business glowing, following a magnetic field that lurches through space like something wounded. The glow shifts, breathes, migrates as the field twists through the planet's sideways spin. Same physics as our northern lights, but bent out of shape by a world rotating on its side with its magnetic heart off-center. But the auroras were only the visible edge of something far stranger. The radio emissions. Hidden inside that same field, Voyager 2 heard a whisper. Faint radio crackles rising out of the radio quiet. Not the usual static of a planet, but a rhythmic hiss, a pattern. That signal was electron-cyclotron maser emission, the same process that powers Earth's auroral kilometric radiation. The radio shout our own auroras send into space. Free electrons spiraling down magnetic field lines, amplifying radio waves as they go. Earth's version is loud, unmistakable. Uranus's was so faint it nearly vanished into the noise, barely detectable at the edge of the spacecraft's instruments, and it pulsed in a rhythm nobody predicted. The strongest bursts beat in a 42-hour cycle, keyed to the way the magnetic field sweeps past the sun as the planet rotates. A radio heartbeat from a wounded magnetosphere, telling us the field isn't just tilted, it's alive and in constant motion. This is where the story takes a turn nobody expected. The methane mystery. The trouble started with a simple measurement. Uranus's upper atmosphere is carrying far more methane than Neptune's, and no one can say why. Methane is heavy. It ought to sink. On both ice giants, methane should condense and settle downward, draining out of the visible sky. Neptune mostly behaves. Uranus doesn't. Its upper haze holds onto methane at concentrations that defy the settling that should pull it down. That stubborn methane is a fingerprint. It points to a planet built differently, a world whose deep layers mixed and churned in ways Neptune never experienced. The composition isn't random. It's a record of how and where this planet first formed, written into the air itself. But the methane wasn't just sitting there, it was moving. The winds. Now picture the wind itself. At Uranus's equator, the air races backward, against the planet's spin, while at mid-latitudes it surges forward with it, some lanes topping out near 560 miles per hour. On Earth, that much shear would tear a storm system apart within days. Here, it holds steady, decade after decade. The tilt is what does it. With the pole facing the sun for 21 years at a stretch, the jet streams get forced into shapes no model predicted, stacked and twisted along the planet's weird axis. And what those winds revealed is something we're still trying to model. The energy budget. But the winds raised a harder question. A planet in equilibrium gives back almost exactly the sunlight it absorbs. Uranus radiates just 1.06 times what it takes in. Barely above the line, compare Neptune, 2.6 times. Two ice giants, born the same way, and one runs an engine while the other has gone quiet. Somewhere inside Uranus, there should be leftover heat from formation, contracting and releasing energy. It isn't showing up. The planet's core is somehow keeping its temperature to itself. But Uranus wasn't done yet, not even close. The seasonal models. So we built the simulations, run the clock on an 84-year orbit, and the seasonal models do strange things, shuttling energy from one pole to the other as the sun swings overhead. The models, a few degrees of tilt changes everything, flipping which hemisphere gets bombarded and when. The planet's weather sits on a knife's edge, balanced on that sideways spin. And all the while, the simulations keep failing to reproduce what we already measured. The heat that should be there, the winds that shouldn't hold. Every correction just moves the error. And this is the part where we realized we'd been asking the wrong question. The comparison. Put Uranus next to Neptune and they seem like siblings. Nearly the same size, nearly the same composition. Two planets born from the same cloud of gas and ice. And yet they behave like total strangers. Neptune churns with storms that outrun the speed of sound, radiates more heat than it takes in from the sun, and cracks the sky with supersonic winds. Uranus sits there, calm, cold, silent, barely leaking any of its own heat at all. For years, the textbooks blamed the tilt. A sideways planet, they argued, would just take light from the sun and spread it unevenly, damping the weather. But the more closely we looked, the less the tilt explained. The two worlds share too much and differ too much for a tilt alone to cover it. The real difference, we'd come to learn, runs root deep, through the interior, through the very chapter of gravity and magnetism and time. What nobody knew at the time was that Uranus had a twin we'd never see. The ice giant class. Neptune and Uranus aren't just two odd planets. They're the only known members of an entire category, a class apart from the gas giants we grew up memorizing. Jupiter and Saturn are mostly hydrogen and helium, huge and light, with no real surface to speak of. Uranus and Neptune are smaller, denser, built around thick mantles of water, methane and ammonia. Ices, we call them, though they're crushed into a hot, slushy, alien state at pressures hundreds of thousands of times our own atmosphere. That distinction gave these two a name of their own, ice giants. For the longest time, that was a class with exactly two members, a footnote in the textbooks, a curiosity. But that's the thing about a class of two. You assume the rarity says something about the universe. It doesn't. The galaxy is full of them, and Uranus is our only map. The exoplanet connection. Because when astronomers aimed their telescopes at distant stars and watched for the dimming of a passing planet, ice giants kept showing up. Again and again. They turn out to be among the most common worlds in the Milky Way. Thousands of them, orbiting stars we can only ever see as points of light, worlds we will never touch, never send a probe to, never photograph up close. Statistics tell us they're out there. Nothing else does. Every one of those worlds is a question with no answer, and every one of those answers we now suspect is hidden in the one ice giant we do know. Uranus is not a strange outlier of our neighborhood. It is the only key we have to a population numbering in the billions. The whole framing flips. This isn't the story of one sleepy, sideways planet at the edge of the familiar. This is where the story takes a turn nobody expected. The formation debate. Two stories compete to explain where Uranus came from. In one, it formed more or less where it orbits today, in the cold quiet of the outer solar system, pulling itself together from whatever ice and rock drifted by. The other story is harder to swallow. It says Uranus grew much closer to the Sun among the giants, and then migrated outward, pushed by gravity and debris as the whole system rearranged itself. Each version leaves its fingerprints. A planet born in place keeps a certain composition. A planet that traveled carries the scars of the road, a different mix of ices, a different spin, a different history in its very bones. And this is the part where timing became everything. The NICE model. In the 1990s, a team of astronomers in Nice, France, proposed an answer we had never considered. The giant planets did not simply form and stay put. They migrated, scattering thousands of icy bodies as they went. That churning triggered a violent reshuffling known as the Late Heavy Bombardment, when comets and planetesimals rained down on the inner worlds. And in that chaos, Uranus and Neptune likely traded places, swapping orbits like two hurried passengers. It is an elegant explanation for a solar system that otherwise looks too tidy. Yet it carries a brutal consequence for our sideways planet. But if that migration happened, it should have left Uranus in pieces. The survival. Think about what that journey would demand. A planet shoving through a field of debris, millions of miles from home, taking endless impacts. Its moons should be jumbled, its rings broken, its spin knocked every which way. Instead, Uranus is almost insultingly orderly. Its rings are fine and exact. Its moons circle in a flat, patient plane. Whatever it endured did not scramble the geometry of the place. Some force or some luck kept it whole through a ride that should have destroyed it. The more closely we look, the more the planet seems to have been protected, held together by something we still cannot name. But Uranus wasn't done yet, not even close. The Kuiper connection. Look at the moons, the irregular ones, the dark ones, the ones orbiting backwards. They don't match the neat families a planet's own gravity would sculpt. Their composition points somewhere else entirely, to the frozen reservoir beyond Neptune. That's the Kuiper belt, and Uranus reads like it passed straight through the middle of it. Spectral signatures on the darkest moons and the fine, charcoal-colored dust in its rings match objects out there almost grain for grain. This wasn't simple distant resemblance. This was contact. The planet swept the early trans-Neptunian region clean, accreting whatever icy debris drifted into its path and carrying the evidence of that collision-zone childhood with it, even now, billions of years and billions of kilometers later. And what that debris field left behind is something we're only beginning to understand. The Trojans. There's a kind of object that should have survived that ride. Trojan asteroids, locked into Uranus's orbit itself, balanced at the Lagrange points ahead of the planet and behind it, where gravity holds them in place for the age of the solar system. Every giant planet has them. Jupiter carries thousands, some of them larger than small countries. Uranus should hold its own share, leftovers from the same crowded region that fed its moons. Yet every search has come back empty, nothing at the leading point, nothing trailing behind. Either the collisions that churned this neighborhood were too violent for a stable population, or the Trojans wandered off on paths we simply haven't traced yet. The sky still holds the answer, waiting for a telescope with the patience to find it. But the real mystery wasn't what orbited Uranus, it was what happened inside it. The core question: we've never seen the planet's center, and we're not certain what's even down there. Most worlds assemble around a dense, rocky core, and the models say Uranus has one too. But Voyager's gravity data left a loose thread it couldn't pull. The pull this planet exerts on a passing spacecraft is shaped by how its mass is arranged, top to bottom. The measurements match a sharp, buried core. They also match a slow, gradual fade, where mantle and core blur into one another with no clean boundary to name. If there's no distinct core, then the planet isn't really a ball with a center at all. It's a gradient, a continuous transition from cold, thin atmosphere to something dense and unclassified. 2 readings, 2 Uranuses, and no instrument flown close enough to break the tie. This is where the story takes a turn nobody expected. The density clue. Weigh the whole planet and you know its bulk density, and that number is precise. Uranus comes out at about 1.27 grams per cubic centimeter, barely denser than water, and from that alone, the mass budget divides cleanly. Roughly 63% of it should be ice, mostly water, methane, and ammonia, about 24% rocky material, and a surprisingly thin 13% hydrogen and helium wrapped around the outside. The numbers are confident. The structure underneath them is not. Density tells you proportions, not arrangement. Is that ice layered in discrete shells, or churned into a single muddy ocean miles deep? Does the rock sit as a compact core, or shatter into slurry? Every allowed interior reproduces the same weight on the scale. 3 different Uranuses, all consistent, all impossible to rule out from afar. And this is the part where we realized we needed to go back. The mission that never was. Going back is not a new idea. For decades, mission planners have sketched orbiters for this world, and each one died on paper. Oceanus, a dedicated Uranus orbiter concept. Herschel, another sweep. The ice giant mission, studied again and again, engineered in slide decks and PowerPoints, never in orbit. The reasons compound. Uranus sits 19 times farther from the Sun than Earth, a build that demands a launch window that opens roughly once every dozen years. Travel time alone swallows a decade or more, and after all that, the spacecraft must slow down against an atmosphere it must then survive. The cost climbs past the point where committees flinch, and for decades, the flinch won. Other targets, closer ones with cheaper tickets, kept jumping the line. Uranus stayed a ghost in the margins, a place we understood only through one brief flyby in 1986. But the tide was finally shifting. The decadal priority. In 2023, the National Academies issued its Planetary Science Decadal Survey, the document that sets NASA's priorities for the next 10 years. On that page, one mission was ranked above all others, the highest priority large flagship of the entire decade. A dedicated Uranus orbiter and atmospheric probe. The numbers, the structure, the seasons, the tilt, the moons, all of it folded into a single comprehensive campaign. It is no longer a wish list entry. It is the official roadmap, the thing the community chose to do first. Planners are already counting on gravity assists and scheduled arrival windows late in the next decade's calendar. Nothing is launched yet, and budgets still loom, but the direction is set. The case has been made, voted on, and written into the plan. And what that mission is designed to find is the answer we've been circling for 40 years. The probe. About 50 years after we first flew past it, a machine the size of a small desk is designed to fall into Uranus. There is no landing on an atmosphere like this. There is only a descent. From the moment its heat shield bites into the hydrogen and helium, the probe measures composition, temperature, pressure, and wind speeds as they tear it apart. It is a first direct sampling of an ice giant, the only one besides Neptune that exists to be sampled at all. The descent lasts about an hour, maybe less depending on where the winds carry it. Somewhere below the clouds, the signal simply stops, but the probe will only survive for an hour. The orbiter has to do the rest. The orbiter. That orbiter is built for years, not an hour. Over the course of a multi-year tour, it swings past every major moon, dozens of them, each flyby a separate rendezvous between gravity and momentum. The magnetosphere gets mapped in 3 dimensions. The rings are photographed edge-on, and radar sounds through the crust to look for water below the ice. Every instrument tuned for a world nobody has ever studied this closely. Where the probe falls, the orbiter circles. Where the probe dies, the orbiter keeps its appointments. This is where the story takes a turn nobody expected. The magnetometer. Central to it all sits the magnetometer suite, a set of sensors built to do what every previous mission could only guess at: map Uranus's magnetic field in full 3-dimensional detail. The field is tilted and offset, lopsided in a way no other planet replicates. The question has always been whether the mantle structure causes it, or whether something deeper, nearer the core, shapes that strange asymmetry. Those measurements finally separate the 2 possibilities. Half a century of models get tested against one set of real numbers, and this is the part where we'll learn if Uranus is unique, or just the first example. The ice penetrator. So the orbiter carries more than instruments. It carries a smaller craft. An ice penetrator aimed at Ariel or Titania before the main spacecraft ever arrives. A few tens of kilograms of hardened metal that hits the surface and burrows, sampling the subsurface ice it was never meant to survive. If the readings come back clean, we learn where organics form and where they don't. If they come back rich, we find a second ocean world with chemistry that looks a lot like a starting point. Either way, it's a probe that stays put and tells us what the ice has kept secret for 4 billion years. And this isn't just planetary science. It's a search for the kinds of molecules that preceded life here, frozen at 19 AU and waiting for the first visitor to break the seal. That's the hope driving the whole architecture. A surface-touching mission, not just a flyby. But the science return depends on one thing: launch windows. The gravity assist. Uranus sits nearly 3 billion kilometers out, and no rocket alive can throw a spacecraft that far in a straight line. The mission needs a gravity assist, and it needs Jupiter. The giant's pull can bend the trajectory and add the extra velocity that saves a decade. That kind of alignment isn't common. The window opens in the early 2030s, and it closes fast. A few years where the geometry works, and Jupiter is exactly where the math needs it to be. Miss the orbit, and the numbers stop adding up. Planetaries call it a once-in-a-generation opportunity, and they are, if anything, understating it. The next real chance lands in the 2040s, and then the 2050s after that, each one slipping further from the people who planned the first attempt. And if we miss it, we wait another decade. The power problem. There's a second problem that the trajectory can't fix, and it's power. At 19 AU, sunlight arrives at about 1/400th of what it does on Earth. The panels that keep a Mars rover alive would put out a trickle here, not even enough to keep the heaters running. So the spacecraft will carry radioisotope thermoelectric generators, RTGs, blocks of decaying plutonium that turn heat into electricity with no moving parts and no dependence on the sun. They've kept Voyager alive for nearly half a century, so the technology is proven. It's also finite. The United States produced its last fresh supply of the fuel in the late 1980s, and every decade since, missions have pulled from a shrinking inventory. Each launch consumes grams of it, and the stockpile doesn't grow. Uranus is competing with Mars rovers and deep space flagship probes for the same scarce resource, and there isn't enough to fuel them all. But RTGs are in short supply, and Uranus isn't the only mission that needs them. The budget reality. So the decadal survey made its call. Uranus orbiter and probe, the top priority flagship for the decade. priced at about $4.02 billions. That recommendation carries real weight. It tells NASA where the community wants its flagship money spent. But here is the quiet truth of how funding actually works. A priority ranking is not an appropriation. NASA's planetary science budget runs around $3 billion a year, and most of it is already spoken for. Mars sample return is chewing through billions with nothing to show yet. Dragonfly is in build. Europa Clipper just launched. The pile of committed money keeps growing, and the share left for a brand new flagship gets thinner each cycle. History does not flatter the fine print. The last decadal's #1 recommendation, Mars sample return, is now being redrawn at a fraction of its original scope. A priority ranking is a map, not a check. The budget reality is that a $4.02 billion flagship needs sustained political buy-in across administrations, and that is a far scarcer resource than plutonium. The committee can rank Uranus first. Congress holds the purse strings, and that gap between what science demands and what the budget will tolerate is where This Is the Story takes a turn nobody expected. The international option. It doesn't have to be a one-country project. For the right mission, agencies pool what they do best. One nation builds the orbiter, another contributes the instruments, a third supplies the launch vehicle. The cost of reaching Uranus gets split across several budgets, and every partner gets a share of the science. The European Space Agency has already proven the model, flying Cassini-Huygens to Saturn and placing a probe beneath the clouds of Titan. Japan's JAXA has deep experience with planetary magnetospheres, precisely the instrument Uranus needs most. Even modest contributions, a single instrument or a ride to orbit, can turn a mission that looks impossible into one that barely fits. There's precedent for this kind of patience. These programs take decades to negotiate, align, and fly, and they build momentum one signed agreement at a time. What looks like a dead end for one nation looks like a beginning for several. But even if the funding aligns, there's one question we can't answer from Earth. The habitability question. Habitability is a word astronomers use carefully because it asks something enormous of a place. Every moon around Uranus is a frozen, cratered world, bathed in light 40 times dimmer than our own. But there is a distinction science has learned to make. On the surface, a world can be barren. 10 kilometers beneath it, the story can change entirely. Modelers now think Ariel and Titania may keep a liquid layer under their ice, warmed not by sunlight, but by the slow, patient decay of radioactive elements in their rock, and by the gravitational tug of their own planet. No probe has ever sampled those depths, so we cannot call it proof. But we have seen this pattern before. Europa, Enceladus, Ganymede, all of them looked like dead rock from above. All of them hide oceans that we now suspect could be teeming. A confirmed liquid layer on any moon of Uranus would mean the list of potentially habitable places in our solar system does not end at Jupiter and Saturn. It doubles, maybe more. And this is the part where Uranus stopped being a curiosity and became a destination. The ocean worlds. We've spent decades hunting ocean worlds across the solar system. Europa, 3,000 kilometers of ice shell over a salty sea. Enceladus, ice geysers spraying into space from its south pole. Titan, rivers of liquid methane beneath a thick orange sky. Each one famous, each one funded, each one a candidate for the kind of water that makes life possible. The recipe has 3 ingredients: liquid water, an energy source to drive chemistry, and the elements themselves. Most worlds have 1, maybe 2. Ariel has 2 confirmed already: smooth young terrain and water ice exposed at its surface. And the third, the energy, seems to be hiding just below. Nobody built a mission to Ariel, not in the same way we built missions to Europa. The Voyager data sat for decades, filed, reviewed, and mostly ignored. But once you start counting ocean worlds in the Uranian system, the tally stops being a surprise. Titania, Oberon, Ariel, maybe more, 4 or 5 moons that could each hold a liquid ocean. And Uranus wasn't done yet, not even close. The cryovolcanism evidence. Look closer at Ariel, and the surface stops looking quiet. There are smooth plains where impact craters should be, old craters wiped clean, replaced by fresh terrain. Bright deposits streak the floors of deep chasms, and long, sinuous channels wind across the crust, winding and branching like liquid once carved them. These are the signatures of cryovolcanism, not molten rock, but something colder, water, mixed with ammonia and methane that stays liquid far below the freezing point of pure ice. It erupted, flowed, and refroze, resurfacing Ariel within the lifetime of the solar system. The key word is recent. Those smooth plains are geologically young, wiped clean maybe 500 million years ago, perhaps less. On Voyager's grainy frames, that means Ariel has been active while dinosaurs walked the Earth, and volcanoes like that don't switch off overnight. What nobody knew at the time was that the eruptions might still be happening. The hidden oceans. Those cracked crusts are the tell. When a small moon wobbles and flexes, the surface cracks, and whatever sits beneath shows through. The chemistry of Ariel's bright deposits, the pattern of its craters, the way Titania and Oberon carry their own deep fractures, all of it points the same direction. Beneath those frozen surfaces, kept liquid by the lingering heat of ancient collisions, sit oceans. The impacts that left the moon's battered early crust also delivered the warmth that keeps water moving today, millions of miles from the sun in permanent darkness. We can read the evidence from orbit, the chemistry at the vents, the way heat escapes, the ages of the resurfaced plains. But each measurement reaches us at an angle, from a planet tilted 98 degrees, its poles aimed at the sun and its moons orbiting sideways. But reading those oceans from 90 degrees of tilt means eyes we haven't sent yet, and the geometry of the solar system is about to slam that window shut. The closing window. A spacecraft heading for Uranus can only get there by riding a gravity assist through Jupiter, and that alignment lines up once every 12 years. The next sweet spot lands in the early 2030s, and the mission studies, the design work, the cancelled flagships, they all revolve around a single date. Miss it, and the science loses more than time. Every orbit, every reading of a tilted magnetosphere, every map of those sideways moons has to be replanned around a planet whose seasons stretch across decades. The probes that could have flown are already retired on paper, replaced by studies that point at a calendar. And hidden inside that frozen deadline is the reason Uranus matters more than any planet we've ever visited. A reason that has nothing to do with the tilted ice we can see. The common majority. Because out among the stars, statistical surveys of exoplanets keep returning the same picture. Ice giants are the most common kind of planet in the galaxy, more numerous than rocky worlds like Venus or Earth, more numerous than the gas behemoths we name first. They are the galaxy's default setting. And Uranus is our only specimen of an entire dominant class. One tilted world standing in for billions of others we've only glimpsed as a dimming star. Every planet we've landed on, every atmosphere we've tasted, belongs to a minority. The majority is ice, and we've held it up to the light exactly once. But a planet type that common almost certainly carries oceans with it, which quietly turns the nearest frozen world into biology's most important question. The life question. If the hidden oceans of Uranus's moons can host chemistry, then ice giants, not rare blue marbles, are the galaxy's most likely cradle for life. A probe could settle it. Magnetometers would feel the churn of salt water through 1,000 meters of ice, mapping currents the surface has never broken. Spectrometers would taste the vent chemistry at the surface, sniffing for the molecules that mark life's raw machinery, the same signatures we hunt for on Europa and Enceladus. Each result would close a door or swing one open, narrowing the odds to something we could actually count on. The verdict is still out, because it has to be, but the journey is already circling the answer, and the ice has kept its secret for 4 billion years. So the whole mission loops back on itself. A world knocked sideways, a family of hidden oceans, a closing launch window, all bound to a mystery the ice has kept sealed for 4 billion years. The question that remains, so we end where we began, a single planet, tipped onto its side, its magnetic field dragged out of shape, oceans hidden under ice, a launch window closing. Most worlds declare themselves loudly. Uranus barely whispers. Yet that whisper might matter more than any supernova. If the most ordinary-looking planet in the cosmos hides liquid water beneath the quiet, then water is not a miracle. It is the default. Life would no longer be a rare accident in a lucky corner of the galaxy. It would be a thing that happens wherever the chemistry allows, and the chemistry allows almost everywhere. The real question isn't whether we can reach Uranus by 2045. It's whether the most forgettable world in the solar system is the one keeping the score on how common life truly is. If you found this one part of the story worth your night, the rest of the series is waiting. Subscribe, and we'll keep walking the cosmos together.